Hello and welcome. Tonight we'll be exploring the very first stars that ever shone in our universe. Long before planets drifted through quiet solar systems, before galaxies unfolded into graceful spirals, and before the atoms that would one day become oceans, mountains, forests, and even ourselves had been forged, there was another generation of stars. They lived fast, burned brilliantly, and disappeared almost as quickly as they arrived. Yet despite their brief existence, they quietly changed the future of everything that followed. Their story is not only the beginning of astronomy, but in many ways it is also the beginning of our own. So, find a comfortable place to rest, allow your thoughts to slow, like gentle waves reaching a quiet shore, and together, let's begin a peaceful journey into one of the oldest chapters the universe has ever written. On a clear night, far away from the bright lights of cities, you can still look upward and find yourself surrounded by thousands of tiny points of light. It is a view that has inspired wonder for countless generations. Long before telescopes or spacecraft existed, people looked toward the stars searching for stories. They connected bright lights into familiar shapes, imagining hunters, bears, dragons, ships, and heroes stretching across the darkness. Every civilization found its own meanings among the same stars. Those ancient observers could never have imagined that each tiny point of light was a world entirely different from the next. To human eyes, the stars appear almost identical. They twinkle softly, scattered across the sky like grains of silver dust. But appearances can be wonderfully deceptive. Imagine walking through a vast forest at twilight. From a distance, every tree blends into a single dark canopy. Only when you step inside do you begin to notice the incredible variety. Some trees are young and slender, others are ancient giants. Some bloom for centuries, while others grow quickly before falling back into the earth. The night sky is much the same. What seems like a simple collection of lights is actually an enormous family filled with extraordinary diversity. Some of the smallest members of this family never quite become true stars at all. Astronomers call them brown dwarfs. You might think of them as nature's almost stars, objects that gathered enough material to begin forming but never quite reached the conditions needed to shine like our sun. Rather than failures, perhaps it is kinder to imagine them as quiet beginnings that simply followed a different path. Far more common are the gentle red dwarfs. These small, cool stars are the patient gardeners of the universe. They burn their fuel so slowly that many will continue shining for trillions of years, far longer than the universe has even existed so far. While our own sun enjoys what might be considered a comfortable middle-aged life, many red dwarfs are only just getting started. Our sun belongs to another family known as yellow dwarfs. Despite feeling familiar to us, stars like our own are not the most common at all. They are something of a pleasant middle ground, warm enough to nurture life on nearby worlds, yet calm enough to shine steadily for billions of years. It is easy to think of the sun as ordinary simply because it is our nearest neighbour, but in truth every star carries its own unique story. As stars become larger, they also become increasingly dramatic. Giant stars swell to enormous sizes, while supergiants grow so immense that if one replaced our sun, its outer layers might stretch far beyond the orbits of several inner planets. Even beyond these remarkable objects lie the rare hypergiants, among the largest stars ever discovered. They are so luminous that they constantly shed enormous amounts of their own material into space, almost as though the star is slowly dissolving into the universe around it. Yet even these magnificent giants are only passing visitors. The brighter a fire burns, the faster it consumes its fuel. A tiny candle may glow softly throughout the evening, while a roaring bonfire blazes brilliantly before fading much sooner. Massive stars follow the same quiet rule of nature. Their tremendous brightness comes at the cost of surprisingly short lives. Eventually every star reaches its own ending. Some gently release their outer layers, leaving behind beautiful glowing clouds and a tiny white dwarf at their centre, slowly cooling over unimaginable ages. Others meet far more dramatic fates, collapsing into incredibly dense neutron stars. A few spin with astonishing precision, becoming pulsars that sweep beams of energy through space like distant cosmic lighthouses. Rarer still are magnetars, whose magnetic fields are almost beyond imagination, capable of producing bursts of energy powerful enough to briefly outshine entire galaxies. And then there are black holes, places where gravity becomes so overwhelming that not even light can escape. They often capture our imagination more than any other object in the universe, inspiring books, films, and endless curiosity. If someone asked which of these extraordinary objects is the rarest, many people might choose the black hole, or perhaps the magnetar. It would seem like a sensible answer. Yet the universe has one more surprise waiting. Long before red dwarfs quietly filled the galaxy, before yellow stars like our sun were born, before even the first galaxies had fully matured, another generation of stars briefly illuminated the darkness. They belong to no familiar neighbourhood we can visit today. They formed in a universe that contained almost nothing except hydrogen and helium, before heavier elements existed, before rocky planets could form, before life had even the smallest possibility of emerging. Astronomers call these ancient pioneers Population 3 stars. The name sounds technical, but the idea is beautifully simple. Imagine tracing your family tree backward through parents, grandparents, and countless earlier generations until you eventually reach your oldest known ancestors. Population. 3 stars are something like the great-grandparents of every star we see today. The stars surrounding us tonight, including our own sun, are part of a long cosmic family whose roots stretch back to these forgotten pioneers. For many years, scientists believed these first stars were forever beyond our reach. They lived quickly, disappeared long ago, and left behind only faint clues scattered across the universe. Astronomy has a remarkable habit of turning impossible questions into patient investigations. With every new telescope, every clever observation, and every improvement in technology, those ancient lights seem just a little less distant. To understand how we came to know that these mysterious stars ever existed, we first need to discover how humanity learned to read the hidden language written inside starlight itself, a language that quietly reveals what stars are made of, how they live, and even how old they may be. As you continue gazing into the night sky, something curious begins to happen. Those countless stars no longer seem like anonymous points of light scattered at random. Instead, they begin to feel like individuals, each carrying a story that has unfolded over millions or even billions of years. But this raises a gentle question. How could anyone possibly know the story of a star that is so far away it can never be touched? For most of human history, the answer was simple. We could not. Ancient civilizations admired the stars with remarkable dedication. Farmers relied upon them to mark the changing seasons. Sailors trusted them to guide ships across vast oceans. Priests and scholars carefully recorded their movements, believing the heavens reflected a deeper order hidden within the world below. The stars became calendars, navigational tools, and characters in countless myths. Yet despite all this careful observation, people knew almost nothing about what stars truly were. Were they tiny fires? Were they holes in a great celestial sphere? Were they eternal lights placed in the heavens by divine hands? For thousands of years, these questions remained beautifully unanswered. Everything began to change in the early 17th century, when an Italian scholar named Galileo Galilei pointed one of the first telescopes toward the sky. His instrument was simple by modern standards, but its impact was extraordinary. The hazy ribbon of the light we call the Milky Way suddenly dissolved into countless individual stars. Tiny points that had blended together now stood apart, revealing a universe far richer than anyone had imagined. It was as though humanity had spent its entire life looking at a distant forest through morning mist, only for the fog to quietly lift. Where there had once appeared to be a single blur, countless individual trees now merged, each with its own place in the landscape. Telescopes continued to improve over the centuries. Astronomers mapped the positions of stars with increasing precision. They discovered that many stars traveled together in pairs, quietly orbiting one another over enormous stretches of time. Others gathered into clusters, while entire galaxies slowly revealed themselves beyond our own. But perhaps the greatest breakthrough came not from building larger telescopes, but from asking a different question. Instead of simply looking at where a star was, scientists began asking what its light could tell them. At first glance, starlight appears simple enough. It shines softly against the darkness, sometimes white, sometimes blue, sometimes orange or red. Yet hidden inside that gentle glow is an astonishing amount of information. Imagine receiving a handwritten letter from someone you've never met. Even before reading the words, you might notice the handwriting, the paper, or the ink. Tiny details quietly reveal something about the writer. Starlight behaves in much the same way. Every beam of light carries a subtle signature left behind by the star that created it. Rather than ink upon paper, the message is written across light itself. During the 19th century, astronomers developed a remarkable technique known as spectroscopy. Although the name sounds complicated, the idea is wonderfully simple. When starlight is spread into its rainbow of colours, it is not perfectly smooth. Fine dark lines appear across the colours, almost like delicate fingerprints. Each chemical element leaves behind its own unique pattern. Hydrogen produces one pattern, helium creates another, iron leaves its own unmistakable signature. By studying these delicate markings, astronomers could begin identifying the ingredients hidden inside stars without ever travelling to them. For the first time in history, humanity had learned to read the language of light. One of the pioneers of this new approach was an Italian astronomer named Angelo Secchi. As he carefully compared the light from thousands of stars, he noticed that stars with similar colours also shared similar patterns within their light. This allowed him to group stars into families based not on where they appeared in the sky, but on their physical nature. It was a quiet revolution. The constellations that had guided humanity for thousands of years remained beautiful, but they no longer defined the stars. Science had begun revealing relationships far deeper than imagined shapes drawn across the heavens. A few decades later, another remarkable chapter unfolded at the Harvard College Observatory in the United States. There, a group of women worked tirelessly examining thousands upon thousands of photographic plates containing tiny images of stars. At the time, they were simply known as the Harvard Computers, a title that reflected careful calculation long before electronic computers existed. Among them were Williamina Fleming and Annie Jump Cannon, whose extraordinary dedication transformed astronomy forever. Night after night, plate after plate, they patiently organised stars according to the patterns hidden within their light. Annie Jump Cannon eventually refined the classification system into one that astronomers still use today. Rather than memorising a confusing collection of labels, you can simply imagine stars arranged like a long temperature scale, beginning with the hottest blue stars and gradually cooling toward the gentle red ones. Even so, astronomers still believed that stars were fundamentally quite similar. They assumed that the differences between them were mostly matters of temperature, like kettles of water heated at different degrees. Then another brilliant scientist quietly challenged that idea. Her name was Cecilia Payne. Working during the 1920s, she carefully analysed the light from the sun in far greater detail than anyone before her. Her calculations led to a startling conclusion. The sun was not made mostly of the same materials found on Earth, as many scientists had assumed. Instead, it was composed overwhelmingly of hydrogen, with helium making up most of what remained. Everything else, including familiar elements like carbon, oxygen, iron and calcium, existed only in tiny amounts. At first, this conclusion seemed so surprising that many leading astronomers doubted it. Even Cecilia Payne herself hesitated, wondering whether such an unexpected answer could possibly be correct. Yet only a few years later, further observations confirmed that she had been right all along. It was another gentle reminder that nature often proves stranger and more beautiful than our first expectations. Not long afterward, astronomer Walter Baade noticed something equally intriguing. Stars near the graceful spiral arms of the Milky Way contained larger amounts of heavier elements, while much older stars inhabiting the galaxy's outer regions appeared remarkably poor in those same materials. This discovery gave birth to a new way of thinking. Instead of viewing all stars as members of one enormous family living identical lives, astronomers realized that stars themselves belong to different generations. The youngest stars, rich in heavier elements, became known as Population 1. Older stars containing fewer heavy elements became Population 2. And almost immediately an even deeper question emerged. If there were young stars and old stars, could there have been an even earlier generation? A generation born before the universe had been enriched with carbon, oxygen, iron, or any of the other elements that would one day build planets and people? The answer, scientists suspected, was yes. Somewhere in the unimaginable past, hidden beyond the reach of ordinary observation, there must have been a first generation. Not simply older stars, but stars born into a universe so young that almost nothing yet existed except hydrogen and helium. Finding those ancient pioneers would become one of astronomy's greatest adventures. But before we can follow that search, it helps to imagine the universe itself before a single star had ever begun to shine, when darkness stretched across space, waiting patiently for its very first dawn. If the earliest astronomers had possessed a magical telescope capable of looking farther than any instrument we can build today, they might have imagined that the universe would simply continue forever, filled with stars in every direction. It seems like a reasonable expectation. After all, wherever we look today, the cosmos is alive with light. Galaxies sparkle by the trillions, stars are born inside glowing clouds of gas, and planets quietly circle countless distant suns. But if we continue travelling backward through time, something remarkable begins to happen. The familiar universe slowly starts to disappear. Galaxies become fewer, stars become rarer. Eventually, even the brightest lights fade away. If we could keep drifting farther into the past, there would come a moment when the universe contained no stars at all. It would not be an empty universe, nor would it be a lifeless void. Instead, it would be a quiet place, waiting patiently for the first spark of cosmic dawn. To understand this strange era, we must journey almost 14 billion years into the past, not long after the Big Bang. The Big Bang is often imagined as a tremendous explosion, but it is perhaps more helpful to picture it as the rapid unfolding of space itself. Every region of the young universe expanded together, carrying matter and energy with it, like raisins slowly separating inside a rising loaf of bread. There was no central point from which everything burst outward. Space itself was growing. During its earliest moments, the universe was unimaginably hot. Nothing resembling stars or galaxies could exist. Matter was packed so tightly, and temperatures were so extreme that even atoms could not hold themselves together. But the universe was expanding, and as it expanded, it cooled. Just as a cup of tea slowly loses its warmth while resting on a table, the young cosmos gradually became calmer. After several 100,000 years, something extraordinary happened. The temperature finally fell enough for tiny particles to combine into the first stable atoms. Most of these atoms were hydrogen, the simplest element in nature. Almost all the rest became helium, along with the faintest traces of lithium. The heavier elements that are so familiar today, carbon, oxygen, silicon, iron, and all the others, did not yet exist. the universe was astonishingly simple. If you could have gathered all its ingredients into a single recipe, it would have been remarkably short. Hydrogen, helium, a whisper of lithium, and little else. At that moment, another ancient traveller also began its endless journey. Light. For the first time, light could move freely across space without constantly colliding with matter. That ancient glow has never disappeared. Even today, billions of years later, astronomers can still detect its faint warmth. They call it the cosmic microwave background, but you might simply imagine it as the oldest surviving photograph of the universe, a gentle afterglow from its infancy that still surrounds us in every direction. Yet despite the presence of this ancient light, the universe soon entered an age of remarkable darkness. There were no suns, no galaxies, no glowing nebulae, no familiar constellations, only vast oceans of invisible gas stretching farther than imagination can comfortably follow. Astronomers sometimes call this period the Cosmic Dark Ages. The name may sound dramatic, but it describes a universe that was simply quiet. It was less like a frightening darkness and more like the peaceful silence before sunrise, when the world is still asleep and the first birds have not yet begun to sing. Nothing seemed to be happening. But beneath that calm surface, invisible forces were already shaping the future. One of those forces was gravity. Gravity is wonderfully patient. It never rushes. It simply continues its work moment after moment, drawing matter together with quiet determination. Scattered throughout the young universe was something even more mysterious than ordinary matter: dark matter. Despite its name, dark matter is not known to be made of darkness, nor is it invisible dust floating through space. In truth, scientists still do not know exactly what it is. They know it exists because of the gentle gravitational pull it exerts on everything around it. You might imagine hiking across a landscape hidden beneath thick morning fog. Although you cannot see the hills and valleys beneath your feet, you can still feel yourself walking uphill or downhill. In much the same way, astronomers cannot see dark matter directly, yet they can observe how its invisible landscape quietly guides everything else. Long before the first stars appeared, dark matter had already gathered into enormous invisible clumps. These became the universe's first gravitational shelters, quietly collecting clouds of ordinary hydrogen and helium. Very slowly the gas drifted inward. The clouds became denser. Gravity pulled a little harder. More gas arrived. Everything happened with extraordinary patience. But forming a star is not as simple as allowing gravity to squeeze a cloud together. As gas falls inward, it also becomes warmer. You may have noticed something similar while using a bicycle pump. As air is compressed, the pump grows warm beneath your hand. The same gentle principle applies across the universe. Compressing gas naturally produces heat. That heat creates a problem. Warm gas resists being squeezed further. It pushes outward, trying to halt the collapse. Gravity pulls inward, while heat quietly pushes back. For a star to be born, some of that heat must escape. Today, this process is surprisingly efficient. Modern clouds of gas contain many different elements that act like tiny cooling systems, carrying energy away into space and allowing gravity to continue its patient work. But the first universe had no such luxury. There was almost nothing except hydrogen and helium. Only tiny hydrogen molecules could help carry away heat, and they did so far less efficiently than the rich mixture of elements available today. It was rather like trying to cool a warm house by opening only a single small window instead of every door and window at once. Because cooling was so difficult, most gas clouds simply could not continue collapsing. Only the truly enormous clouds possessed enough gravity to overcome the warmth building inside them. These immense clouds continued shrinking, growing denser and hotter over hundreds of thousands of years. Deep within their hidden centers, pressure steadily increased until, at last, nature crossed an invisible threshold. hydrogen atoms began joining together. The first fusion reactions quietly ignited. After hundreds of millions of years of darkness, the universe welcomed its first sunrise. Those first stars did far more than simply illuminate the cosmos. They announced the beginning of an entirely new age, one in which light, chemistry, galaxies, and eventually life itself could begin their long and remarkable journey. They would burn unlike any stars that followed, and although their lives would be astonishingly brief, their influence would echo across every generation of stars yet to come. When the first stars finally appeared, the universe crossed a quiet but profound threshold. For hundreds of millions of years, space had been a vast and peaceful darkness, filled mostly with drifting clouds of hydrogen and helium. Then, almost imperceptibly at first, tiny islands of light began to bloom across that endless night. These were not ordinary stars. In fact, if one of them could somehow be placed beside our own sun, the difference would be almost impossible to ignore. Imagine placing a small candle beside an enormous lighthouse. Both produce light, yet the scale is completely different. In much the same way, many astronomers believe that the first generation of stars dwarfed the stars we know today. Some may have contained dozens of times the mass of our Sun. Others may have reached 100 times the Sun's mass, or perhaps even more. Although modern computer simulations continue to refine these estimates, nearly all agree on one remarkable point. The universe's earliest stars were among the most massive ever born. Why would the first stars grow so enormous? The answer begins with the unusual simplicity of the young universe. Today, clouds of gas are surprisingly rich. They contain countless elements forged by earlier generations of stars. Carbon, oxygen, silicon, and many other atoms help gas clouds cool efficiently, allowing them to break apart into many smaller pieces. Each fragment may eventually become a separate star, much like a large loaf of bread being divided into many small rolls before baking. The first universe could not do that. Its clouds contained almost nothing except hydrogen and helium. Without many efficient ways to release heat, the gas resisted breaking into smaller fragments. Instead of producing hundreds of little stars, enormous amounts of material continued falling toward only a few growing centres. It was rather like watching rainwater collect across a smooth stone. Instead of forming many tiny puddles, the water gradually flows together into a handful of much larger pools. As more gas gathered, these young stars became astonishingly heavy. But tremendous size always comes with a hidden cost. Earlier we compared different stars to candles and bonfires. Now that comparison becomes even more important. Imagine placing two piles of firewood side by side. One is small enough to keep a family warm throughout the evening. The other is a towering stack that burns with roaring flames bright enough to illuminate an entire hillside. The larger fire is certainly more spectacular, but it also consumes its fuel much faster. Stars follow a similar rhythm. A small star burns quietly, carefully using its fuel over extraordinarily long periods of time. A giant star lives differently. Its enormous gravity squeezes its central region so intensely that the temperature rises to extraordinary levels. Under those conditions, hydrogen is transformed into helium at an astonishing pace. The star shines with breathtaking brilliance, but every moment of that brilliance uses up part of its precious fuel. You could think of it as the difference between someone strolling peacefully through a beautiful garden and another person sprinting across an open field. Both eventually reach their destination, but one arrives much sooner because every step is taken with greater intensity. The first stars live their lives at a sprint, while gentle red dwarf stars may continue shining for trillions of years, and our own sun is expected to enjoy a lifetime measured in many billions of years. Many population 3 stars may have survived only a few million years before reaching their final moments. By cosmic standards, that is scarcely more than the blink of an eye. Yet during those brief lives, something extraordinary was happening deep within their brilliant hearts. Every second, unimaginable pressures gently encouraged hydrogen atoms to join together, producing helium while releasing enormous amounts of energy. That energy slowly worked its way outward, eventually escaping as the light that illuminated the ancient universe. As the supply of hydrogen gradually diminished, the stars began changing. Helium itself became new fuel. Later still, even heavier elements began forming inside the hottest and most massive stars. Carbon, oxygen, neon, magnesium, silicon. Each new stage was a little shorter than the last, almost like the final chapters of a story unfolding more quickly as it approached its ending. Eventually, many of these stars began producing iron within their central regions. Iron is unusual. Unlike the earlier stages of stellar fusion, building heavier elements beyond iron does not provide additional energy to support the star against its own immense gravity. It is rather like reaching the final support beam inside a towering building. Once that beam can no longer carry the weight above it, the entire structure becomes unstable. The collapse begins almost instantly. For some stars, the ending produced one of the greatest explosions the universe has ever witnessed. These tremendous supernovae briefly outshone entire young galaxies. In only a few moments, they released more energy than our Sun will produce throughout its entire lifetime. Some of the largest population 3 stars may have experienced something even rarer. Astronomers call these pair instability supernovae, although the name itself is less important than the remarkable outcome. Instead of leaving behind a dense remnant, the entire star may have been completely torn apart. Nothing remained except an expanding cloud carrying newly forged elements into the surrounding universe. It was a spectacular ending, but also an extraordinary beginning. Every atom of carbon released into space would one day help form future stars. Every atom of oxygen might eventually become part of distant oceans. Every atom of silicon could someday build rocky planets. Every atom of iron might one day become part of mountains, meteorites, or even the flowing blood inside living creatures. Other massive population 3 stars appear to have followed a different path. Rather than exploding completely, their enormous weight may have caused them to collapse almost directly into black holes. These were not the gigantic black holes found today at the centres of mature galaxies, but they may have been important seeds from which those enormous cosmic giants eventually grew. It is a fascinating thought. Some of the supermassive black holes observed by modern telescopes may owe their existence to stars that lived during the universe's earliest dawn. Even now, astronomers continue debating exactly how massive population 3 stars truly were. Some computer simulations suggest that many formed alone. Others indicate they may have been born in small groups, with several giant stars sharing the same cloud. Still others raise the intriguing possibility that alongside the giants, a few much smaller stars may also have formed. If so, some of those quiet survivors might still exist today, hidden somewhere within our galaxy, patiently waiting to be discovered. Science often grows stronger through questions rather than certainty, and population 3 stars remain one of astronomy's most exciting mysteries. Each new telescope, each improved simulation, and each careful observation helps sharpen the picture, even when the complete story remains unfinished. What seems beyond doubt, however, is that these ancient giants permanently transformed the universe. Before they were born, the cosmos was chemically simple, built from only the lightest ingredients. After they lived and died, space became richer, more complex, and filled with the raw materials needed for entirely new generations of stars. Without realizing it, the first stars had quietly become the universe's earliest master builders, preparing everything that would come after them. The lives of the first stars were remarkably brief, especially when compared with the immense age of the universe. Some may have shone for only a few million years before disappearing forever. It might seem surprising that such short-lived objects could leave a lasting mark on cosmic history. Yet sometimes the smallest chapter in a story changes everything that follows. Imagine dropping a single pebble into the centre of a perfectly still lake. The pebble itself quickly disappears beneath the water, but the ripples continue spreading long after it is gone, reaching shores that seem impossibly far away. The first stars were like those pebbles. They vanished long ago, but the ripples they created are still moving through the universe today. Before these ancient giants were born, the cosmos was wonderfully simple. Almost every atom belonged to either hydrogen or helium, with only the faintest traces of lithium. If you had tried to build a rocky planet, you would have found nothing suitable. There was no carbon to form complex molecules, no oxygen to combine with hydrogen into water, no silicon to build stone, no iron to create planetary cores. The ingredients that make our world feel familiar simply did not exist. It is almost impossible to imagine Earth without rocks, oceans, mountains, or the air we breathe. Yet the young universe knew nothing of these things. Everything began to change inside the blazing hearts of population 3 stars. As these enormous stars aged, they became extraordinary cosmic workshops. Layer by layer, their interiors quietly transformed simple elements into increasingly complex ones. Carbon emerged first, followed by oxygen, neon, magnesium, silicon, and eventually iron. Each new element represented another step in the universe's slow journey toward complexity. You might imagine an artist beginning with only 2 colours of paint. At first, the possibilities seem limited, but by carefully blending those colours again and again, countless new shades gradually appear. Before long, a canvas that once seemed almost empty becomes rich with depth, texture, and beauty. The universe was painting in much the same way. Hydrogen and helium were only the starting colours. Everything else would have to be created. When the first stars reached the ends of their lives, those newly formed elements did not remain trapped inside them. Powerful explosions scattered them across surrounding space, enriching enormous clouds of gas that had once contained almost nothing except the simplest atoms. Astronomers often describe this process as chemical enrichment. The phrase may sound technical, but the idea is beautifully straightforward. Each generation of stars leaves behind gifts for the generation that follows. Imagine an old forest at the end of autumn. Leaves fall gently onto the ground where they slowly break apart. Over time, they enrich the soil, allowing fresh plants to grow stronger the following spring. The older trees never truly disappear. Instead, they quietly become part of the next generation. Stars behave in a remarkably similar way. Population 3, stars enrich the cosmic soil. From that richer material, a new generation of stars slowly emerged. These became what astronomers call population 2 stars. Unlike their ancient ancestors, they formed in clouds already containing small amounts of heavier elements. The universe had begun learning new ways to build. Generation after generation, this quiet cycle continued. Stars were born, stars lived, stars died. Each generation added more heavy elements to the surrounding gas. Each generation handed more possibilities to the next. Eventually, after countless cycles of birth and renewal, stars like our own Sun appeared. The Sun belongs to population 1, the youngest large family of stars in our galaxy. Compared with the first stars, it formed in an astonishingly rich environment. By then, billions of years of stellar recycling had filled the Milky Way with carbon, oxygen, nitrogen, silicon, iron, calcium, phosphorus, and many other elements. Those elements gathered into clouds. The clouds formed planets. On at least one small planet, chemistry slowly became biology. It is a breathtaking chain of events. Without the first stars, there would have been no heavy elements. Without heavy elements, there would have been no rocky planets. Without rocky planets, there would have been no oceans, mountains, forests, or living cells. In a very real sense, every living thing owes a quiet debt to those forgotten pioneers. The influence of the first stars reached even farther than chemistry. Their brilliant light also transformed space itself. Earlier, we visited the cosmic dark ages, that peaceful era when the universe contained no stars. Once population 3 stars ignited, they flooded nearby space with intense light. That light carried enormous amounts of energy, gradually changing the surrounding hydrogen gas. Rather than imagining this as a complicated physical process, picture a winter landscape just before dawn. Frost covers every field and everything appears still. As the sun slowly rises, warmth spreads across the ground. Ice begins melting, streams begin flowing, and the landscape awakens. Something similar happened across the universe. The first stars slowly awakened the cosmos. Region by region, their powerful light transformed the vast clouds of hydrogen surrounding them. Over hundreds of millions of years, more and more stars joined this quiet work until enormous regions of space had been reshaped. Astronomers call this period the epoch of reionization, but perhaps it is easier to think of it simply as the universe waking from its long night. As space became more transparent, light could travel greater distances. Galaxies continued growing. New stars appeared in ever larger numbers. The once dark universe became increasingly luminous. At the same time, another remarkable transformation was taking place. Some of the black holes left behind by the first giant stars continued gathering surrounding gas. As more material spiraled inward, these young black holes grew larger and larger. Given enough time, some may have become the enormous black holes now found at the centres of galaxies, including our own Milky Way. Even today, astronomers continue investigating exactly how these colossal objects formed so quickly after the Big Bang. Population 3 stars remain one of the leading pieces of that fascinating puzzle. The story becomes even more humbling when we consider ourselves. The calcium that strengthens your bones, the iron carried through your blood, the oxygen filling your lungs with every quiet breath, the carbon forming every cell in your body. Each of these atoms was forged inside stars that lived long before our sun existed. Some may trace their ancestry through countless generations of stellar recycling, but every one of those family trees eventually reaches back toward those first brilliant giants that illuminated the young universe. The phrase, "we are made of stardust," is often repeated because it sounds poetic. Yet, it is also remarkably accurate. Every atom heavier than hydrogen and helium has passed through the heart of at least one star. As you rest beneath tonight's sky, surrounded by the quiet glow of familiar constellations, it is comforting to remember that the universe is not simply a collection of distant objects. It is a continuous story of transformation. The first stars did not merely shine for a little while before disappearing. They became part of everything that followed, quietly weaving themselves into every galaxy, every planet, every ocean, every tree, and every living creature that would one day open its eyes beneath the stars. As remarkable as the first stars were, one question has quietly lingered in the minds of astronomers for decades. Did every one of them disappear? Or could a few still be shining somewhere in the darkness, hidden among the hundreds of billions of stars that fill our own galaxy? At first, the answer seemed almost obvious. If population 3 stars were as enormous as scientists believed, then they must all be gone. Massive stars live extraordinarily fast lives. Even the longest lived among these ancient giants would have exhausted their fuel billions of years ago, leaving behind only black holes or the faint echoes of their spectacular explosions. For many years, this appeared to settle the matter. The first stars had lived. The first stars had died. Their story was over. Yet science has a wonderful habit of becoming more interesting whenever better evidence arrives. As computers became increasingly powerful, astronomers began creating far more detailed simulations of the young universe. These virtual universes allowed researchers to follow the slow collapse of primordial gas clouds with far greater realism than ever before. Instead of watching only one enormous star emerge, something unexpected sometimes appeared. The giant cloud occasionally began breaking into several smaller pieces, not hundreds of fragments, as often happens in the modern universe, but enough to produce families of stars rather than a single lonely giant. Imagine watching a river flow around a large rock. At first, the water appears to move as one smooth stream, but look more carefully, and you notice smaller currents branching away, circling gently before joining together again farther downstream. The birth of the first stars may have unfolded in a similar way. Gravity still gathered enormous clouds of gas, but the flow of that gas was more graceful and more complicated than astronomers once imagined. Instead of feeding only one growing star, it sometimes shared its material among several neighbouring companions. This possibility changed everything, because while the largest stars would still burn themselves out very quickly, some of their smaller companions might have lived very different lives. To understand why, it helps to think about trees. A giant redwood grows quickly, towering above the forest in only a relatively short time. A much smaller tree grows, more patiently, adding only a little height each year. Although the giant seems far more impressive, the slower growing tree may survive long after the towering giant has fallen. Stars follow a similar rhythm. Large stars consume their fuel with breathtaking speed. Small stars are wonderfully economical. They burn gently, patiently, carefully. Some are capable of shining for periods so long that the universe itself is not yet old enough for them to have reached the end of their lives. If even a handful of low-mass population 3 stars formed during the universe's earliest dawn, they could, in principle, still exist today. That possibility has transformed astronomy into something resembling an enormous treasure hunt. But finding such survivors would not be easy. Imagine searching for the oldest handwritten book in the world after it has spent thousands of years inside a busy library. Countless hands have touched it. Dust has settled upon its pages. Repairs may have been made. New bindings might cover its ancient paper. The original book still exists. But time has left its fingerprints. Astronomers face a similar challenge. A surviving population 3 star would have spent billions of years travelling through the Milky Way. During that immense journey, it would not have remained perfectly untouched. Tiny amounts of gas and dust drifting through space could slowly settle onto its surface. Scientists sometimes describe this process as surface pollution. The phrase sounds unfortunate, but the idea is surprisingly gentle. Imagine discovering an antique bronze statue buried beneath centuries of dust. The dust does not change the statue itself. It simply hides its original appearance until someone carefully brushes it away. Likewise, a surviving population 3 star may have collected a thin outer layer containing heavier elements that were never part of the star when it first formed. That makes identifying these ancient survivors extraordinarily difficult. Fortunately, astronomers know where to begin looking. Most of the younger stars in our galaxy occupy the graceful spiral disk of the Milky Way. Our own Sun is one of them, quietly orbiting the galactic centre among countless neighbouring stars. The oldest stars, however, often follow very different paths. Many travel through the vast spherical region surrounding the galaxy, known as the galactic halo. If the Milky Way were compared to a great city, the bright spiral disk would resemble its busy streets, filled with constant activity. The galactic halo, by contrast, would be more like the peaceful countryside surrounding that city, where ancient things are often left undisturbed for far longer. That makes the halo one of the most promising places to search for the oldest surviving stars. Modern space missions have become invaluable partners in this search. One of the most important is the European Space Agency's Gaia spacecraft. Rather than taking dramatic photographs, Gaia performs an extraordinarily patient task. It measures the positions and motions of nearly 2 billion stars with astonishing precision. By carefully tracking how stars move through space, astronomers can identify those that follow unusually ancient orbits, especially stars passing through the galactic halo. these become excellent candidates for closer study. Yet motion alone is not enough. Researchers must also examine the light from each candidate star, searching for the faintest hints about its chemical history. If a star contains extremely small amounts of heavy elements, it may preserve a valuable record of the early universe. Not every ancient-looking star turns out to be a genuine survivor from the first generation. Most belong to population 2, the second generation of stars that formed shortly after the first giant supernovae enriched the cosmos. Even so, every extremely ancient star discovered becomes another important clue. Each one teaches astronomers a little more about conditions during the universe's earliest chapters. Sometimes science advances not by finding exactly what we hoped for, but by steadily narrowing the possibilities. A star that is almost primordial still helps us understand the stars that came before it. And so, the search continues. Somewhere among the hundreds of billions of stars surrounding us tonight, there may be a quiet survivor whose light has travelled through nearly the entire history of the universe. It may look completely ordinary to the eye, no brighter than countless neighbouring stars, yet inside it could still preserve memories from an age before galaxies fully matured, before planets existed, and before the universe learned how to build the rich diversity of elements that surround us today. Finding such a star would be like discovering a living witness to the universe's earliest morning. A patient traveller that has carried its story across almost 14 billion years, waiting for someone at last to recognise it. By now, you might be wondering how astronomers can search for something that has almost certainly disappeared. Unlike paleontologists, they cannot dig into ancient rocks. Unlike historians, they cannot uncover forgotten books or buried cities. The first stars left behind no written records, no visible monuments, and perhaps not even a single surviving giant that we can point to with confidence. And yet, scientists have learned that the universe has its own kind of archaeology. Instead of excavating the ground beneath their feet, they carefully examine the light arriving from the sky. Imagine visiting an ancient village after everyone has long since departed. The houses may be gone, but scattered pieces of pottery remain beneath the soil. A few weathered tools lie hidden among the stones. Perhaps the outline of an old fireplace can still be seen. None of these discoveries tells the entire story by itself, but together they slowly reveal the lives of people who vanished thousands of years ago. Astronomers work in much the same way. Rather than searching directly for the first population 3 stars, they search for the quiet traces those stars left behind. Every ancient star discovered today is a fragment of pottery. Every unusual chemical pattern is another broken piece waiting to be understood. One of the greatest tools in this investigation is something we have already encountered: the remarkable language hidden inside starlight. Whenever light passes through a telescope and into a scientific instrument, it can be gently separated into a rainbow of colours. Within that rainbow lie delicate patterns, almost like the fine grooves of a fingerprint. Each chemical element leaves behind its own distinctive mark. Hydrogen speaks with one pattern, helium with another. Carbon, oxygen, magnesium, calcium and iron each leave their own quiet signatures. Reading these patterns is rather like listening to an orchestra. Even if dozens of instruments are playing together, an experienced musician can still recognise the sound of a violin, a flute, or a cello. In the same way, astronomers learn to recognise the presence of different elements, even when all their signals are woven together inside a single beam of light. Among all these elements, one has become especially important: iron. This is not because iron is the most abundant heavy element, nor because it is the most interesting. Instead, it serves as an extraordinarily useful guide. Iron produces many clear and recognisable signatures in starlight, making it an excellent starting point when searching through millions of stars. Imagine standing on a quiet beach after the tide has gone out. If you wanted to find a rare seashell, you would probably begin by scanning the sand for anything unusual before bending down for a closer look. Astronomers do something remarkably similar. They first search enormous surveys containing millions of stars, looking for those with unusually little iron. A star that contains very little iron is unlikely to belong to the youngest generations of the universe. Instead, it may have formed before many heavy elements existed. Such stars become exciting candidates for further investigation, but the search does not end there. Finding a metal-poor star is only the beginning. Large telescopes around the world are then turned toward these promising candidates. Their light is examined in far greater detail, allowing astronomers to measure not only iron, but dozens of other elements as well. The goal is to reconstruct the history of a star in much the same way that a detective reconstructs an event from scattered clues. Did this star form after one supernova? Several supernovae? Or perhaps after only one enormous population 3 star enriched the surrounding gas? Each possibility leaves behind a slightly different chemical pattern. These patterns are sometimes called chemical fingerprints, but they can also be imagined as family recipes passed quietly from one generation to another. Suppose every family in a village baked bread using a slightly different recipe. Even centuries later, someone studying those recipes might discover which families were related, who learned from whom, and how traditions spread over time. Stars preserve similar family recipes within their chemical compositions. Every element tells part of the story. Together, they reveal ancient relationships stretching back almost to the beginning of time. One particularly remarkable discovery captured the attention of astronomers around the world. Researchers identified one of the most iron-poor stars ever discovered. Rather than remembering its long catalogue number, it is easier to think of it simply as one of the oldest chemical time capsules known to science. This star contains astonishingly small amounts of iron, suggesting it formed when the universe was still in its infancy. Yet something about its chemistry seemed unusual. Instead of matching the material expected from many generations of stellar evolution, its composition appeared consistent with enrichment from perhaps only a single massive ancient star. It was as though one lonely population 3 giant had lived, exploded, and quietly enriched a nearby cloud from which this second-generation star was born. Although this remarkable object is almost certainly not itself a population 3 star, it may preserve one of the clearest surviving records of one. Moments like these remind scientists that sometimes the closest clue is not the object we seek, but its immediate descendant. Of course, interpreting these ancient records is rarely straightforward. Earlier we spoke about surface pollution, the slow accumulation of tiny amounts of material onto a star over billions of years. Astronomers must carefully account for this possibility. Powerful computer models help estimate how much a star's surface may have changed during its long journey through the galaxy. They compare many different scenarios, testing whether the observed chemical pattern reflects the star's original composition, or whether later events have gently altered its appearance. This process requires enormous patience. There is rarely a single observation that settles the question. Instead, understanding grows little by little, as evidence from many different stars begins pointing toward the same conclusion. It resembles assembling a giant mosaic from thousands of tiny stones. Each new discovery fills another small gap. One piece alone reveals very little, but over time, an increasingly clear picture begins to emerge. Thanks to decades of careful work, astronomers have now identified numerous extremely ancient stars scattered throughout the halo of the Milky Way. None can yet be confirmed as a surviving population 3 star, but together they paint an increasingly detailed portrait of the universe's earliest generations. Every observation narrows the possibilities. Every spectrum becomes another page in a history book written not with ink but with light. And perhaps that is one of the most beautiful aspects of astronomy. The universe rarely gives away its oldest secrets all at once. Instead, it invites us to slow down, to observe carefully, and to appreciate that even the faintest glimmer of starlight can carry memories from nearly the beginning of time. Those quiet messages continue arriving every night, crossing unimaginable distances with extraordinary patience, waiting for someone to learn how to read them. By this point in our journey, it may seem as though astronomers are trying to solve an impossible mystery. The first population 3 stars lived nearly 14 billion years ago. Most likely they burned brightly for only a few million years before disappearing forever. If they are truly gone, how could anyone hope to observe them today? The answer is both elegant and wonderfully creative. Sometimes, instead of looking directly at something, you search for the effects it leaves behind. Imagine walking through a quiet forest just after sunrise. You may never see the deer that pass through during the night, yet its footprints remain pressed into the soft earth. Broken branches, fresh hoof prints, and gentle trails through this grass quietly tell you that it was there. Astronomers often work in exactly the same way. The first stars may have vanished billions of years ago, but they left footprints across the universe. Modern telescopes are becoming increasingly skilled at finding those ancient traces. One of the most remarkable discoveries in recent years began with what looked like an ordinary distant star. Astronomers named it Earendel, a name inspired by ancient literature that means morning star. Its light began travelling toward us when the universe was still very young, only a small fraction of its present age. By the time that light finally reached Earth, it had spent billions of years crossing the expanding cosmos. Ordinarily, a single star at such an extraordinary distance would be far too faint to observe. Yet nature provided an unexpected helping hand. Between Earth and Earendel lies an enormous cluster of galaxies. The combined gravity of that cluster gently bends the surrounding space, causing light travelling through it to change direction. Rather than imagining complicated mathematics, picture placing a glass marble on top of a page of printed words. The letters beneath the marble appear stretched and enlarged because the curved glass bends the light passing through it. The universe can perform a similar trick. Massive clusters of galaxies act like gigantic natural magnifying glasses. They bend and amplify the light from even more distant objects hiding behind them. This phenomenon is known as gravitational lensing. Without it, Earendel would almost certainly have remained invisible. Although Earendel itself is probably not one of the first population 3 stars, its discovery demonstrated something incredibly encouraging. Individual stars can be observed at astonishing distances. If one star can be found, perhaps others may eventually follow. This possibility has become even more exciting with the arrival of the James Webb Space Telescope. Unlike many earlier telescopes, James Webb was designed to observe the universe in infrared light. As the universe expands, light travelling across billions of years gradually stretches into longer wavelengths. By the time the oldest starlight reaches us, much of it has shifted beyond the range visible to human eyes. Infrared instruments allow astronomers to recover these ancient messages. It is rather like listening to someone speaking from the opposite side of a vast valley. Their voice becomes softer and deeper with distance, yet with sensitive enough equipment, the conversation can still be heard. James Webb has already revealed galaxies that existed surprisingly early in cosmic history. Some appear brighter, larger, and more mature than many scientists expected. Inside these distant galaxies may lie regions where population 3 stars once formed. Astronomers carefully study the combined light from these galaxies, searching for unusual patterns that might reveal the presence of extremely hot, chemically primitive stars. So far, no observation has provided absolute confirmation, but several candidates have generated considerable excitement. Each new observation narrows the search. Each new spectrum teaches scientists a little more about what the first stellar populations may have looked like. James Webb is not working alone. The Hubble Space Telescope continues contributing valuable observations, while future observatories promise even greater capabilities. The Nancy Grace Roman Space Telescope will survey enormous regions of the sky with extraordinary efficiency, helping astronomers discover many more distant galaxies. Meanwhile, the extremely large telescope, currently under construction on a mountaintop in Chile, will possess a mirror so vast that it will gather far more light than any previous optical telescope. With such remarkable sensitivity, astronomers hope to examine the earliest galaxies in unprecedented detail. Yet surprisingly, some of the most valuable clues may not come from visible light at all. Earlier, we visited the cosmic dark ages, when neutral hydrogen quietly filled the young universe. As the first stars ignited, their intense radiation carved growing bubbles through that ancient hydrogen. Imagine standing outside during the first snowfall of winter. Overnight, a smooth blanket of snow covers an open field. Then, as morning sunlight slowly warms the landscape, patches begin appearing where the snow melts first. From above, the once unbroken white surface gradually resembles a piece of Swiss cheese, with open holes expanding farther and farther across the field. Astronomers believe something similar happened throughout the young universe. The first stars created expanding bubbles of transformed hydrogen. As more stars formed, those bubbles grew larger. Eventually they overlapped until nearly the entire universe had awakened. Future radio observatories, including the Square Kilometre Array, hope to map this ancient hydrogen directly. Instead of photographing the stars themselves, they will attempt to observe the changing pattern of hydrogen spread across enormous regions of space. It would be rather like reconstructing a campfire by studying the warmth still lingering in the surrounding ground after the flames have gone out. Another entirely different messenger has recently joined this remarkable investigation. Gravitational waves. These are tiny ripples travelling through space itself, produced whenever enormous masses accelerate in particularly dramatic ways. The first direct detection of gravitational waves transformed astronomy by allowing scientists not only to see the universe, but also to listen to it in an entirely new manner. Today, observatories such as the Laser Interferometer Gravitational Wave Observatory, more commonly known as LIGO, can detect collisions between black holes that occurred billions of light years away. Future missions, including the planned Laser Interferometer space antenna, will extend this ability even further, becoming sensitive to slower and more massive cosmic events. Some astronomers hope these instruments may eventually detect black holes descended from the first generation of stars. Others wonder whether unusually massive mergers could preserve subtle clues pointing back toward population 3 stars. The stars themselves may have vanished long ago, yet their descendants continue moving through the universe. Their explosions reshaped galaxies. Their black holes may still collide. Their light transformed cosmic hydrogen. Their chemical fingerprints remain written inside younger stars. Like footprints preserved in ancient stone, these quiet traces continue guiding scientists toward a time when the universe experienced its very first sunrise. And with every new telescope, every careful observation, and every patient advance in technology, those distant echoes grow just a little clearer, gently bringing us closer to meeting the first stars at last. As our journey slowly draws towards its quiet conclusion, it is worth returning to the simple question that first brought us here. How can astronomers discover the universe's first stars? At first, the question seemed almost impossible to answer. The oldest stars lived billions of years before our own sun was born. Most likely they disappeared long before planets like Earth even existed. No telescope can simply point toward the sky and watch one of those ancient giants shining in real time. And yet, little by little, humanity has learned to follow their story. Not by chasing the stars themselves, but by following the countless traces they left behind. Every ancient star with unusually simple chemistry, every distant galaxy whose light has travelled almost the entire age of the universe, every cloud of hydrogen that remembers the first great awakening of cosmic light, every black hole that may have begun its existence inside one of those forgotten giants. Together, these scattered clues slowly form a picture that grows clearer with each passing year. Perhaps the most remarkable lesson is that the first stars never truly vanished. Their original light faded long ago, but their influence continues to flow through everything that followed. Imagine an elderly gardener planting a tiny orchard. The gardener may never live to enjoy the full shade of those trees, yet generation after generation finds comfort beneath their branches. Children climb them, birds build nests among their leaves, their fruit feeds people who never knew the person who planted them. The gardener is gone, the orchard remains. Population 3 stars shaped the universe in much the same quiet way. Their lives were astonishingly brief. Their legacy has lasted almost 14 billion years. Every later generation of stars inherited the elements they created. Those later stars produced even richer collections of matter. Eventually, galaxies became more beautiful and more complex. Planets formed from clouds filled with silicon, magnesium, oxygen, carbon, calcium, iron, and countless other elements that simply did not exist before the first stars began their work. Some of those planets developed oceans. A few may have developed life. One of them became our home. It is easy to think of Earth as something separate from the wider universe. Our mountains feel permanent. Our oceans seem timeless. The trees outside our windows appear rooted entirely in this world. Yet every one of those familiar things carries an ancient cosmic history. The oxygen entering your lungs with each calm breath was forged inside stars. The calcium strengthening your bones was forged inside stars. The iron quietly travelling through your blood was forged inside stars. Even the carbon that forms every living cell within your body began its journey deep inside stellar furnaces long before the Earth existed. When astronomer Carl Sagan famously said that we are made of star stuff, he was expressing one of the most beautiful truths in all of science. It is not simply a poetic metaphor, it is the literal history of our atoms, and if we continue tracing that family history farther and farther into the past, generation after generation, we eventually arrive at the first stars. They were not our direct ancestors in the biological sense, but chemically, cosmically. They were among our oldest ancestors indeed. Even after decades of remarkable discoveries, many questions remain unanswered. How massive were the very first stars? Did most form alone, or were they born in families? Could a few small population 3 stars still be quietly shining somewhere in the halo of the Milky Way? Will the James Webb Space Telescope discover unmistakable evidence of them inside the earliest galaxies? Will future observatories finally reveal the precise moment when the cosmic dark ages gave way to the first dawn? Will enormous radio telescopes complete detailed maps of the universe's ancient hydrogen, allowing us to watch the first bubbles of starlight spreading across space? Could future observations of gravitational waves uncover black holes whose origins stretch all the way back to those first brilliant giants? These questions remain open. Far from being frustrating, that uncertainty is one of science's greatest strengths. Every answer naturally leads to another question. Every discovery opens another doorway. Every generation of astronomers inherits mysteries from those who came before, just as each generation of stars inherited the elements created by earlier ones. In that sense, science itself resembles the universe it seeks to understand. Knowledge grows gradually, patiently, quietly, one careful observation at a time. Perhaps, somewhere in the coming decades, a future telescope will finally capture unmistakable evidence of a true population 3 star. Perhaps astronomers will discover a tiny survivor hiding among the oldest stars of our own galaxy. Or perhaps the answer will arrive in a form nobody has yet imagined. History has often shown that the universe enjoys surprising us. Galaxies turned out to be far more numerous than anyone expected. Black holes proved to be real. Gravitational waves, once considered almost impossible to detect, are now routinely observed. Planets have been found around thousands of distant stars. Again and again, the cosmos has rewarded patient curiosity. There is every reason to believe it still holds many wonderful surprises. And perhaps that is the quiet lesson hidden beneath tonight's story. The universe does not reveal itself all at once. It asks us to observe carefully, to remain curious, to accept that some mysteries require generations of patient work before they finally begin to yield their answers. As you rest beneath tonight's sky, the stars above may appear silent and unchanging, yet each one belongs to a family whose story stretches back through countless generations, all the way to those first luminous pioneers that transformed a simple universe into one capable of galaxies, planets, oceans, forests, and eventually people who could look upward and wonder where everything began. Those first stars burned for only a fleeting moment in cosmic history, but their light in many ways has never stopped shining. It continues in every sunrise that warms our world, in every mountain shaped from ancient elements, in every quiet breath we take, and in every question we ask about the universe that gave us life. And perhaps, as the night grows a little deeper and the stars continue their patient journey across the sky, you can take comfort in knowing that you are not separate from that ancient story. You are one small, beautiful chapter within it, connected by atoms that have travelled across billions of years, carrying with them the memory of the universe's very first dawn. May that thought bring a gentle sense of wonder as your own day comes to rest. Good night, and may your dreams wander peacefully beneath the same timeless stars that have been telling this story since the beginning.